All right, this is page 1 of notes 13 of Calc C, and what we're going to talk about is Euler's method. So Euler's method is a really interesting way of approximating the solutions to a differential equation. So we're kind of used to the idea of using a tangent line, right? So we would, I don't know, you find the derivative, you write the equation of the tangent line, then you just plug into the tangent line, you say it's pretty close to the value of the function, and usually it really is. We also have taken a look at a lot of different Taylor series, right? And we could use a Taylor series, which is like a higher degree tangent thing, right? So it's not a tangent line anymore. It'll be a polynomial that approximates it, and that does a better job than a tangent line. Next thing we're going to do is talk about another way of approximating the solution. It's called Euler's method, and it's actually really, really related to using tangent lines. And it's also an iterative process. So if you just watched the video about Newton's method of approximating the zeros of a function, this is a similar iterative process, but it approximates a different thing. So let's see if we can figure out what to do. So we have all those methods: tangent line, Taylor polynomials. We're going to use Euler's method. We have slope fields. Slope fields are a way of looking at the solution. So what we do here is we're just basically going to do like a Calc 1 problem, and then we'll modify it to an Euler's method problem. So let's see the question. Let's suppose we know that the point 1, 1 is on a function. So that's like your initial condition. We also know that the derivative of this function at any point x, y is given by dy dx equals 2x. Okay. So we're going to pretend that we don't know how to integrate that, just like for the purposes of this, because usually you can't actually integrate, or you don't want to, or whatever, you have your reasons, you know? So we want to approximate 1.2, y of 1.2. So when x is 1.2, what is y? We're going to approximate it. So here's what you would do in Calc 1. You would simply write the equation of the tangent line. So dy dx such that x equals 1 is going to be 2. So our tangent line is y minus 1 equals 2, x minus 1. And then we would say that y of 1.2 is approximately 1 plus 2 times 0.2, so 1.4. Totally fine, right? Like not an issue. But we know we're wrong. And we know because, I mean, this is basically x squared. We know that the original function really looks like that. It's concave up. And then our tangent line, so we know is below the curve. And since the curve is concave up, the curve is like peeling away from the tangent line. So we're wrong, right? And we know that we have an underestimate. And we know kind of, like actually, because it's a Taylor polynomial, we could figure out a bound for how wrong we are. I don't want to do that, but we could. So this is our approximation. So this would be 1. Let's say this is 1.2. So this is what we got. That's going to be 1.2, 1.4. But the real value is up here. And so we went pretty far. We went from 1 to 1.2. What Euler's method says is, what if we didn't go that far? What if instead of going from 1 to 1.2, we did something a little crazier? What if, and this is where it's really similar to Newton's method, what if we only went to 1.1? And we got this as our approximation, and then we just said, like, let's pretend that's on the curve. If that's on the curve, then what I can do is I can write a tangent line, right? So I'm going to pretend that this point is on the curve, and I'm going to write a tangent line. When I do that, I'm going to get a line that's more like this. And so then when I get to 1.2, my approximation will be here, which is closer. That's the whole idea. So it's really similar to Newton's method, where like with Newton's method, you found the x-intercept of the tangent line. You said, like, let's drop that down to the function and say that that's a point on the function, and do a tangent line and find its x, and you keep going. Here, we do something really similar. We say, we'll use a tangent line to find a point on the tangent line. We'll pretend that that point is on the function, and we'll say, let's write the tangent line there and just do it again. And you just keep doing it. And so that's literally Euler's method. So let's see if we can do it and see what we get. So first, we're going to write the equation of the tangent line. Well, we have the equation of the tangent line, right? So dy dx is still 2. So our tangent line is still y minus 1 equals 2, x minus 1. It'd be weird if I got this wrong, right? So we're going to approximate y of 1.1. So y of 1.1 is approximately 1 plus 2 times 0.1, so 1.2. So now we have this point, right? The point is 1.1, comma 1.2. We're going to say this is on the curve. And since we're saying this is on the curve, it's not on the curve, right? But we're pretending that it's on the curve. It's close enough. So what we'll do is we repeat the process. So now we take 1.1 comma 1.2 dy dx such that x is 1.1 is going to be 2.2. So our tangent line, if this point had been on the curve, would be y minus 1.2 is 2.2 x minus 1.1. So it gets more annoying, obviously, to sub in. But, you know, the trade-off there is that it gets more accurate. So, you know, that's kind of how it works. So y of 1.2 should be approximately 1.2. Is that right? 1.2. 1.1 and 1. I feel like I'm saying the same numbers over and over again, but whatever. Times 0.1. So we get 1.4. What's even happening here? 1.42, I think. Okay, so now it's not super closer, but it looks like it's closer. And so that's the idea, right? And like, what if we want it to be more accurate? Well, why not just do it 10 times? So like we're going from 1 to 1.2. So like our delta x is, well, our change in x, we need to go from an initial to a terminal of 0.2, right? That's the distance between them. What if we divided that into 10? So we go 0.2 over 10. Oh my God, 1/5 over 10, 1/50th, right? So you start at 1, you go to 1 plus 1/50th, tangent line, get a point, do it again to 2/50ths, 3/50ths, 4/50, and you just keep going. You'll get a much more accurate thing. So here's like the picture. Also, I feel like that value is wrong. I'm gonna use a calculator and just like confirm it really quickly. Do I even have a calculator open? I don't, but I will in a second. Let's see. And switch to the calculator. Okay, so what did I have? I had y minus 1.2. I don't know why I think this is wrong. 2.2 x minus 1.1, and then such that x equals 1.2. And then, yeah, I got that right. 1.2. What are you doing, brain? Okay, so I got the numerical value correct, I think. So here's a little picture of it in the notes of just like the general idea. The basic idea is in calculus, you want to go smaller amounts than bigger amounts. You don't want to jump over the Grand Canyon. You want to like go, I don't know, smaller things. So you could, with your tangent line, just go like giant. Your delta x here is 0.2. That's really big. That's not even 0.2. What am I doing here? That's 1. This is not a picture of what we were doing. So that fooled me. That whole delta x is 1. If you use your delta x as 0.5, oh my God. If you use delta x as 0.5, you're going to be closer. And you can see here how much closer. Now, a weird thing is like this tangent line here that we've drawn is parallel to like the actual tangent line, which makes sense because we're using the slope. So like it's parallel to the actual tangent line there. Is that always going to be true? I don't actually know that that's always going to be true, because if there's x's and y's, in this example though, it's definitely true. So, and also it's kind of inconsequential to what we're doing, but that's the idea. So use a smaller step size, use more tangent line approximations, you will get a more accurate result. And that's what we're going to do. It's pretty amazing. The really amazing thing is when you use like a lot of them. So let me actually just show you really quickly. I haven't had time or something, or maybe there were technological problems. I don't remember. I haven't had time to put this on the internet yet. This is like an old school GeoGebra file. So you can give it dy dx, so f prime is e to the x in this case. Step size is 0.25, which is not very big. Step 0, what I'm going to do is I'm going to this is it, right? I'm using Euler's method. I'm stepping by 0.5, getting a new point, new tangent line, 0.5 along that, new point, new tangent line, 0.25 along that. I'm saying the wrong number. And you keep going. So if I make this 2, you know, it gets bad, right? Really fast, because 2 is huge. Oh, did I just crash it? Maybe. I don't know what I did. Oh, I'd like double clicked, I guess. So 2 is huge. If we use 1, 1 is smaller. So you can see, and let me just show the solution curve. Way off, right? Because the tangent line, it was below, and then it just keeps getting worse. If I use like 0.1, right? So 0.1, you can see we're like kind of on the solution curve there. And it's going to start to be below because of the concavity, but like pretty good. If we do something like sine of x, let's just do that. Sine of x. And then, so let's do a couple, let's make this 0.2. So one step, tangent view. So new tangent line, go 0.2 along it, new tangent line, go 0.2. And you can see like it does an okay job. 0.2 is a very large step size, in my opinion. Like we should be using something like 0.05, where it's going to be like super tight and looks really good. Computers obviously are very good at this. They're good at iterating things, and that's what this is. So this is just a visualization of what's happening. If I make it like bigger, it'll be bad, like 1. Ugh. Still, I mean, it's not terrible. Like it's not good, but not the worst that it could be. But anyway, I'm gonna go back to the notes. I'll end this here, come back in the next video, do some more. Euler's method, like really cool, not really complicated. Like once you get it down, you're gonna have it. Obviously concavity has something to do with over and under estimates because you're using tangent lines. And when tangent line is involved, concavity tells you over or under estimate. So we're gonna talk about that as well. And I will see you in the next video.